Hello, everyone, and thank you again for attending the TigerGraph and Experial Roundtable on today's topic, which is supply chain. We'll be discussing machine learning, visualization, and more importantly, how does a graph combine with all three of these? Before we get started today, just a few notes. We'll be recording today's session. Should be lots of great content from our speakers today that you see. Very excited, but if you could, at the bottom, there is a Q&A tab. So feel free to go ahead and interject questions as we're going along and as the speakers are talking. We'll save some time at the end and then we'll answer those live and we'll be able to answer those. And then again, if you want to, when we're done, we'll send out a recording at the end of the week with this recording for other folks. So without further ado, Michael Shaler is first up and I'll let you go.
Thank you so much, Scott. My name is Michael Shaler. I run partnerships for TigerGraph, and we have a great partnership with Experial. We're really excited about what we can do together for customers who are looking for supply chain solutions, and we really we think we have a great story to tell. All of our presenters have some outstanding information, so I'll just go ahead and jump in right away. Can't talk about supply chain in 2020 without talking about what's really going on in our world. And one of the things that happened in 8 weeks in the beginning of 2020, in April and May, is that we doubled the rate of change for e-commerce that had taken 10 years, and we did that in 8 weeks. And there's no greater stressor of supply chain than that we've ever seen since World War II. Yes, the GDP is down about 5%, as of the first couple of quarters of the year. E-commerce was up $41 billion. And the two variables that get hit hardest by that are, sourcing lead times and obviously the supply demand variability. Those are, existential challenges for supply chains. And that's kind of where we are in 2020. Click next slide. What we are seeing it for 2021 though is a real focus on building out resilience, building out contingency plans, and having more scrutiny around risk assessment, and then building capacity to kind of resist further shocks to the system and then recover from where we have been. But what we can do now to help supply chain professionals is that we can actually deliver visibility, velocity, and responsiveness. And we do that with graph-enabled supply chain digital twins. And Richard's going to talk about that in the context of Jaguar Land Rover. Velocity in terms of real-time flow, information flows with graph and AI plus ML. And Graham, Brian, and Chris are all going to talk about that. And then where we're really going to go deep is around the responsiveness, where we can take action based on real-time graph analytics and the insights that those generate. So we've got a great start. Click. We just have to get, the vaccine, which has to be transported at -70 centigrade everywhere. And so I think that, we really need globally to overcome all these obstacles and move forward, both in our personal lives and in business. And so we're really excited to be able to do everything we can to help there. Next. So again, I picked up these three themes about see, connect, and act. And, we want to make sure we design the right architecture and build the right pipelines, both from an ingest perspective, as well as from a machine learning perspective and visualization. We want to pick the right methodologies. There's some key graph algorithms and graph queries that really make a big difference here. But then those complement all the work that Graham does, for example, with machine learning. And then, finally, obviously, we need to take action. We need to be flexible and plan for growth. We're going to return and we're going to go even bigger. Next. So we have a roadmap for how to embed, to build out a supply chain digital twin using graph and machine learning and AI. And first, obviously, you want to be able to see it. You want to be able to represent what all the constituents of the data sources and their relationships in the graph. And then the second part is you want to connect that data intelligently. You want to enrich the graph with cost factors, risk factors. You want to score the constraints. Obviously, supply chains are assemblies made of components that are connected to suppliers that have locations and constraints and outcomes and impacts. And so understanding that in context with the interrelatedness of those of that digital twin next leads naturally to the visualization of it. We want to connect deeper through doing two things. One is, giving humans a chance to work with the digital twin, but then also to build out the unsupervised learning capabilities and really drive success in that direction. So see, connect, and then act. We want to use graph plus machine learning to optimize operations and decisions. And that means, we're going to extract features from the graph and feed that into the various algorithms, the various approaches we'll take. Obviously, we can detect communities using Louvain modularity. We can measure similarity between entities, cosine similarity, Jacquard. We can rank the influence of entities. PageRank applies to auto parts in some cases, just in the same way it does to web pages. And then finally, we can do graph embedding with algorithms like node to vector. And then finally, we start to build out the model and then start to iterate. And that's where we really start to see the boost in correctness and insight. Next. So Gartner, of all people, think that this is, absolutely one of the top 10 technology trends of 2020. And when you think about kind of where we fit into this ecosystem of, places where we're pushing it forward, we're going to leverage all of these capabilities in supply chain in the graph. Explainable AI. That's, the graph is the best home for AI solutions. Persistent memory. We run great on Optane and other memory form factors. Blockchain is going to be very powerful once applied to supply chain to ensure certifiability and chain of attestation to ensure that there are no fraud. There's no fraud and there are no imitations. So this picture, again, kind of highlighting the three themes here. Business wants to ask business logic question of their data in the supply chain context. We want to connect that data and we want to take action for supply chain optimization. Click. So a quick note about TigerGraph. We're a startup. We're the only scalable graph native deploy anywhere graph database for the enterprise. And we're founded in 2012. We were in stealth mode for 5 years, and where we have headquarters in Redwood City. The crown jewels of what we do, and this is how kind of TigerGraph and Expero works so very well. Is it comes down to GSQL. We have the ability to integrate with machine learning frameworks, and we also have the ability to integrate with others in a manner that is very powerful. And so we have lots of connectivity. We have lots of capability with our SQL-like language. And quite frankly, I think that the best way to summarize what we do is we answer the best questions about connected data with fast, deep, and wide insights. We're a cool vendor, and we're a wave leader, and we're grateful for the recognition. Click. So in terms of use cases, the business cases, source material management, capacity planning. How do you do inventory optimization and bottleneck detection? These are absolutely fundamental to well-tuned, well-run supply chains, and we want to do everything we can to help customers do even better than they have thus far. The solution pieces by which we can connect both cloud, on-prem. We can have complex visualization. We can do pathing, routing, complex visualizations that are also a way to find root cause and investigations. We have geospatial capabilities, dynamic routing. We have all these capabilities with our joint platform solution that are we think unique. And then finally, in terms of taking action, machine learning and analytics will drive outcomes for recommendations, what if planning and visibility, predictive analytics, and then scoring and risk, and really driving decision tree analytics and audit in ways that are very, very, very powerful. So See, Connect, Act is really kind of what we can help do with supply chains. Click. Here's what the ecosystem looks like. and go ahead and click. You can see that, we have the platform in gray, and all the blue boxes are kind of the core to our graph database. And the two foundations are the graph storage engine, the graph processing engine, and that's how we, achieve scale, performance, and insight through GSQL. We connect to all the data sources on the left, and then we can feed all of the consumption endpoints on the right, and the toolkit is what brings this all together. A database is necessary but not sufficient. The toolkit makes it possible to do things that we're going to see in detail shortly, and it's really exciting. Click. Why is this necessary now? Well, in the age of COVID, we must do more with less, and we're under all this incredible pressure from a supply chain perspective, and we want to make sure that we prevent the risk exposure that a do-nothing approach would take. We want to reduce costs, we want to drive revenue, and we want happier customers in all of this. We all want that. And then we want to ensure that that the disruption and lack of visibility, we can bring an end to that and reduce those risks. The rewards are extreme. We can deploy fast, and then we can actually integrate with your existing technologies to do much, much better than has ever been done before. Click. So now I'm going to hand this off to Chris, who's going to talk about the art of the possible and show us how to increase visibility and optimization. Chris, over to you.
Thanks, Michael.
Thank you.
Okay, so I'm going to show a couple of solutions that we've built on the SDK that we use with TigerGraph and through Expero technology. I'm going to concentrate in these couple of demos around production planning and manufacturing specifically, and really look at data visualization around gaining visibility across the supply chain. So Michael mentioned this representation of a digital twin. We're going to look at a few examples of that manifested within data visualizations. When we look at these types of solutions, they really fall into three main categories. One is just getting visibility, and that's usually challenges around that are due to the fact that this data is sitting in highly latent systems. It's siloed, hard to get to, hard to integrate, hard to resolve from an entity perspective. And that's a huge value add to be able to use TigerGraph basically to just stitch that information together in a coherent way. That really just sets you up to then be able to run traceability around downstream issues, upstream root causes, and start to do analysis. And then that basically remedies what a lot of planning organizations and supply chain leaders are saddled with around old models around optimization. So basically being able to look at this stuff in real time is really the missing link in a lot of the solutions out there. And I'm going to show a couple of examples on how we can use recommendations basically to have that real-time analysis and remediation. And in these three categories of issues really result in a lot of lost revenue, expedite fees, frustrated customers, and then as Michael mentioned as well, with the disruption that we're looking at with COVID-19, it's really breaking down a lot of the historical models. Basically, the profile of supply and demand and some of the things that we thought were constants within the supply chain no longer have application in the past 9 or 10 months that we've been looking at this unprecedented disruption. So things such as capacity or labor that a lot of times we thought were within reason constants in these old optimization models now just don't hold true. We don't have the data to set the precedent basically to be able to look at these things. So now more than ever we need to see real-time analysis within these systems. And so I'll go through a couple of these solutions that we've used with our TigerGraph SDK built with Expero-based visualization tools. We're gonna look at two separate solutions. We're gonna look at one that's more planner workflow, so a remediation workflow, and then the we're going to look at a higher level dashboard for S&OP planning and stakeholder planning. So I'll do the workflow first, and then we'll look into the aggregated dashboard. So I will jump over here. And what I'm looking at as a planner, I'm playing the role as a planner. We're looking at a solution here that one of our customers was basically using to gain visibility over product flow health. So what does the product flow look like through the supply chain from an inventory standpoint and from a resourcing standpoint? Do we have the parts we need to make certain products, and do we have the capacity to take those parts and turn them into the finished goods that we need to along the different stages of the manufacturing process? So that's noted by this flow health indicator. And what this planner would basically do is look at high level KPIs. So this needs that data to be stitched together. This is a case where a lot of the information on this grid is housed in different systems. We're pulling that together through the graph database capability, and then we're basically analyzing through association and relationships what the health indicators are. So we can look at things like what the demand versus production looks like for a given product. And this is mass data, but you can think of each of these line items as a specific product. We can look at what the financials are at risk, what the percent margin is, all those sorts of things to basically give us indicators of where we have some kind of mismatch between demand and production and what the financial results are. Once we pinpoint one of those things, the planner would click into a given product. So I'm looking at a specific product here. And what I'm looking at is its manufacturing journey. So it starts with the active ingredients. In this case, this is a chemical process. So they're basically making a chemical-based product. So they start with active ingredient. It's at certain facilities, suppliers. It then moves to the formulation facilities. Once it's formulated, it's packaged, and then it goes to distribution centers. Each of these small squares here represents a facility. The lines between the facility is basically the movement of material. The thickness is the volume that's moving from location to location. And the color is the overall health of that material moving. So right away, you can start to see that we have bottlenecks between locations. And we can see this through time. Again, all this stuff is stitched together, so we can pretty much walk that hierarchy through, and we can see through traversal of the graph data basically where things start to break down. Now, in a planning situation, we can look at this long term in the future projected analysis, or we can look at this current month or month plus one if we want to do something more tightly coupled, or we can even look at this from a diagnostic standpoint to see this in historical data. But what this basically does is allow me to see the health flow of material through what amounts to a graph basically in this visualization, now that we have all this data linked up together and associated correctly. We can see per line item, per location, what those runs look like here. So this is the material moving on any given location that I select. I can select a time frame. I can select only things that are acutely blocked up, basically. So these are the things that have issues with flow health. I can even look at this from a bill of materials standpoint. So this is my top level finished good, and these are all of the assemblies and sub-assemblies that make that up. So I can basically select a sub-assembly and see where that issue is just for those sets of parts that I selected. So in this case here, I see that I have a bottleneck. And in this case, the planner would basically say, I believe that this is a capacity throughput issue for various reasons. They can basically run a mitigation strategy to rebalance that capacity. And now I'm looking at that specific location and all of the mechanical resources, basically the capacity for the lines that are going to make those products that I selected. and I can see what their profile is from a utilization standpoint. So again, I have high-level KPIs that I can drill into here now that I can aggregate data from disparate sources into the graph. And I can see the schedule for each of the resources that I select. If it's red, it means that for that given month, it's over capacity. There's more scheduled to run on that machine than there is capacity. And by the same token, underneath the line here, when we look at yellow stuff, that means that those yellow points are under capacity. So I have a huge imbalance in my capacity profile month over month. What I want to do is get it in that 85 to 95% utilized, keep those machines running all the time, but not overtaxed. And that's this Goldilocks zone where you see these green dots. So that's interesting. I can basically run a scenario and say, now that I have this information hooked up, I can look at alternative paths, if you will, to route the material through different locations and different resources. And what I'm going to do is tell the system basically to analyze, give me recommendations of movement. So for this resource, it's telling me to move these specific materials. It actually has 76 recommendations. For other resources here, I've only got a couple. And I'm just going to select them all and basically apply them. And I can start to see that it wasn't able to smooth everything out with the heuristics that I provided, but over time, it could basically learn better forms of those heuristics. And I think Graham and Richard, to some extent, will mention that in depth later. But what this has basically afforded me is a starting point. And if I look at what's changed, I can see what the system tried to smooth out here in the scenario compared to the baseline. And I can look in here and see, yeah, in fact, it was able to move a lot of those things to the point where it followed the rules basically to smooth out my production schedule. And I can basically now take this information, the scheduling information, and share it with the factory schedulers or upstream to the stakeholders. So this is a starting point, an example of how recommendations may work around manufacturing within capacity allocation. At a lower level, that's basically a workflow that would be followed by a planning organization. Now we're going to take a look at what that looks like from a higher level. So if I want to basically communicate those things up to a stakeholder within the organization, for example, I can look at a dashboard here. Let's look at something that's a little bit more, even more strategic. A sales and operations planning meeting, for example, we could look at certain KPIs. This would happen on a cadence of monthly or quarterly, for example. And I can start to see what my forecast accuracy and bias is, what the volatility is, again, over time. And now that I have certain indicators, I can even attenuate some of that risk. So if I want to look at how risk is calculated around revenue or around forecasting, because all those things are connected data within the graph, I can start to see the associative risk and configure that in ways where I can say, okay, I don't want to take into account regional disruptions, for example, but maybe supplier confidence is very important and inventory shortage is very important. And it will re-attenuate that risk in real time and start to contextualize the dashboards to see that risk. And even in this application, or this version of that data, we can drill into more detail and we can see what other things, what other sorts of information we can garner. So even at a high level with this dashboard, we could say, what's the demand versus the production peaks and valleys? Well, I want to see it with utilization. I want to see certain KPIs around SLA risks or location. So it affords us a lot of pivots and a lot of ways to look at that associative data because all the relationships are intact. And so just to sum up, the way that we think about this from a visualization standpoint is that we've got this hierarchical set of information, these related bill of materials and inventory types of associations. I think of them as large hierarchies, in essence, a graph. We also have geospatial transportation graphs. They all intersect, and to be able to analyze them in a way that you can see from the standpoint of each of those and how they intermingle, it's really hard to do with relational data in a relational database, that's traditionally used in these types of systems. When you unify this stuff in a graph, you can then start to unlock the natural relationships as they occur in physical space, and you unlock a lot of analytics power. And this also translates to the fact that, for these example use cases, that association boils up to a lot of things that the business is trying to remediate. So there's also a relational effect, not only in physical space or in the data, but also in the way that the organization tries to remedy and remediate some of the disruptions that we've seen specifically now with COVID-19. And then just from just a real quick reference point, this is what an example architecture may look like. So we looked at the user interface part of this and a little bit around the API. Graham and Richard will start to peel back and show how the backend systems basically feed that data and allow us to visualize that. So this is what an example of how the system may manifest itself. We looked at the tip of the iceberg with the demos that I ran, but there's a lot of stuff going on behind the scenes. And with that, I'll hand the baton to Graham, and he can walk through some of the specifics around the machine learning aspects of it.
Thanks, Chris, and thanks, Michael, earlier for setting the stage for us. We want to talk through in this section how the mechanisms operate under the hood, and as Chris just showed in the reference architecture there, we're going to dig into the mechanics of the analytics, the advanced analytics bits. In particular, we'll look at data science and machine learning methodologies, which support some of the workflows Chris went through in his demo earlier. We'll send these slides out after, of course, and we have some references on our website if you're interested in the specifics of the actual inner mechanics of these systems. I want to mention before we get started here that I'm going to be talking about a hybrid system, which is it kind of sits at the intersection of machine learning methods and graph analytics methods. We have a bunch of different algorithms mentioned on this slide. The reason that we have them all aggregated here is because they all work together. They all work in concert. If you already have a system in place that deploys some of these methods, you can use other pieces or other algorithms on this slide and aggregate them all into one system. And I'll show later on how that works. The reason this is important is this. We find across industries, and especially in supply chain, and especially now because, as Michael mentioned, we don't know anything about what's happening these days. I mean, essentially, like, all of our historical information is to some degree or another incorrect in today's operational setting. That when we include graph in the more traditional methodologies, like the machine learning methods that you probably are deploying in your organization, we're able to increase the accuracy of the algorithms we deploy. And then I'll talk at the end of my section about injecting humans or keeping users in the loop so that the information that they see, interpret, and make decisions on is always folded back into these systems as they operate in real time. And when you do that, you've essentially used the power of visualization, graph analytics, and machine learning all together to really create a system that understands the operational setting of your business and can adapt to those changes in real time. I'm going to pick one example here, and there are many, but for the sake of demonstration by way of example, I'm going to talk through an algorithm that we find works exceptionally well and is, as I mentioned before, combines graph algorithms and machine learning algorithms into a common system. And that is the planning optimization for the system that Chris showed earlier. It is a way we recommend plans, schedules, to the users of this system so that when they log in, they don't necessarily have to start from a blank slate. Like, what if we were to try this? What if we were to try this? Which of course they can do. They start instead, because of this system we'll talk about, from a recommended production schedule. And as you can see, and as Chris showed earlier, all the various facets that are included to make that schedule deployable, realizable in the real world are linked together in this product. So let me dig into the details of how that works. First, at a high level, just wanted to mention the sort of inner workings, like how do these systems all talk to each other? And of course, as I mentioned before, the system we're talking about today sits at the intersection of graph analytics and machine learning. And this is what those types of systems do pretty commonly across all use cases in supply chain. So there in number one, we can see that there is a big graph with a bunch of data in it. Of course, those data are related to the physical assets that you have inside your production pipeline. They are related to potentially the labor assets that are included there. And then of course, there is information in that graph database related to the actual production timing, lead times, production schedules, those things. When we move through the analytics process, we see subgraph extraction, which is a big piece of doing analytics to understand where, and that picture in number 2 might be called an ego graph if we were looking at a social network, where we have the relationship of the, I apologize about that, the intersection of the assets with that midpoint. And we take that information and inject it into our machine learning algorithm, which can be one of many things. It could be something very traditional, like what you're probably already using today, or it could be very graph unique, graph novel. And we would call those architectures graph machine learning algorithms. The one that's shown in that box on the bottom there specifically is called a graph convolutional network. And of course, the outputs from our recommendations are surfaced back into the UI. This, on the next slide, is how the system works for the production planning optimization piece. This is, I'm gonna pat our team on the back a little bit here. I think this is very clever. And in fact, it turns out that it works really well. What we have here is a decentralized system with 2 different pieces. This is a reinforcement learning setting, if that's important to folks. And if you want to learn more about this, by the way, we have 2 blog posts on our website that really go into the details about how this thing works. The one system called the trainer is a system which ingests information from the supply chain in real time, right? So that's what's going on with your equipment, when are shipments occurring, when are deliveries happening, and when are conversion steps happening between processes inside of our production pipeline. That trainer continuously, by the way, this is a real-time system, goes through and retrains machine learning agents. So those are like little mini neural networks, and stores those agents inside of a graph database. And what we have on the other side is a business operations simulator. So once we know, because we already have the supply chain modeled in this product, we're able to build simulations which help feed the trainer. And what you have here is this sort of recursive action where you get full adaptive algorithms coming out of this thing. And the reason we care about that at all is because, for instance, if we're going through our day-to-day operations, we have these production schedules on tap, we know where we're going to head, and somebody throws a wrench in the works. Like, for instance, one of our customers decides to decline a large order. That information we can react to, our users can react to in the dashboard, and indeed they will. But interestingly, that information is also ingested into this hybrid graph machine learning system so that it learns about those types of scenarios, e.g. when a large customer cancels a large order, and it begins to understand how to adapt to those types of problems in the future. And the way in which we showcase this to our users and learn not only from the data, like customer cancels big order, but also learn from our users, our supply chain planners, is shown on the next slide, where we have a full interaction between the system and the user. And I'll talk through this here. So, of course, this stuff is based on a TigerGraph database. Information is piped into the reinforcement learning model you saw earlier. Plus, it's also piped into a bunch of other things, right? So one of those things is analytics going on in TigerGraph, right? Recommendations are made not only by one system, like that reinforcement learning model, they're also made by systems like you might already have in place. Like if you already have a planning optimizer, that is an input to this system. If you have a special mechanism which decides whether scheduled production runs are infeasible due to certain business conditions, like, I don't know, for instance, you have a quota for a certain geolocation, like you have to ship a certain number of units to North America. That information, again, is an input to this system. All of those systems feed into the combination system we have here, this hybrid system, and they go through our verification pipeline. And those verification metrics, again, are related to business operational settings, right? Is this really possible? Is this physically reasonable? And that information is what you saw in Chris's demo, that the output is the surfacing of, again, in this one use case I'm talking about, the schedule, the production plan. And when we surface that to the user, as Chris showed earlier, there is a spot for a user to say, this is a reasonable recommendation, or this is not a reasonable recommendation. And that implicit expert knowledge is captured by the system and is used to retrain, as we showed about a slide ago, the system in real time, so that it adapts. The system gets smarter and smarter over time, changes as your business changes. The only other piece here to mention is that the supply chain planners interacting with this system do have explainability metrics they can use inside the dashboard to understand why the recommendations were surfaced. Let me show you a couple of examples, and these are from a couple of different industries. I just think it's important to show what these interactions look like in various contexts. We have a feature ranking list you see there to showcase to supply chain planners, and in this particular example, it isn't that. But the most important rationale for deciding on a production plan. So that would be, conceivably, things that are related to production scheduling, resource allocation, and capacity, et cetera, et cetera. We also have a set of screens there, and you can see this in the upper right, which is meant not for supply chain planners necessarily, but meant for analysts and data scientists to more accurately understand the functioning behind the scenes, why their optimization algorithms are making the decisions they're making. And I won't go into the details here, but if you're interested, please do jump over to our blogs, because we go into depth about that. Okay, let me tell you an example of how this would work. So on the next slide, what we're showing is a set of, just a cartoon about how the supply chain planner would interact with the dashboard you saw to update the system. They can surface information to that system in one of two ways. One is, hey, bad idea, bad recommendation, thanks. The other way is they can actually provide explanatory reasoning. And when they do, that could be something like, hey, you ignored a priority customer. Both of those types of feedback are ingested into our system. And you can imagine, if you're a data scientist, you're probably cringing right now. It isn't all automated, right? There is a fully automated pipeline, which you're showing the bottom there. But there is also an ability for data scientists to jump in and make decisions and alter, let's say, feature engineering pipelines or anything they wish to update that system. I want to showcase like how this really affects the systems in real life. So the next plot we're going to look at here, although it's messy, is an actual example of how the accuracy increases over time in these systems as you include humans in the loop, as you include that expert feedback. Nice chart here, whatever. It doesn't make too much sense without any context. But the important point to note here is that as you increase the number of feedback points you get to this system, the accuracy increases. And you can see there on the vertical scale that we're talking about 10% accuracy in this case, which is amazing. And many customers ask me, what if we don't have time to sit around and wait for all that feedback? Well, it's actually because of the decentralized system I showed earlier, it's actually possible to simulate feedback to estimate how quickly you can expect the system to increase in accuracy. And feel free to reach out after with questions on that. One more thing I'll mention before I turn it over to Richard is that we have, I just wanted to show how these systems are deployed. And it looks like this. So again, this is analogous to that decentralized system. You have to have full pipelines running for inference and then for training, because as you discover new artifacts, whether it's through the automated processes I've discussed earlier or through manual processes, you have to be able to deploy those artifacts into production through machine learning-based CI/CD. And it looks like that. And to summarize all the pieces I've talked about today, on the next slide here, I'm mentioning the 4 sort of overhead bullets, and you need all of this stuff to be able to make these things work. And I'm happy to talk through these things, or you can check out our data products page where all 4 are mentioned. Those 4 being the monitoring of your system, that's both data monitoring and model output monitoring, the CI/CD pipeline to get machine learning tools into production, active learning, which is that fully adaptive recursive training pipeline, and interpretability, which is arguably the most important, which is the ability to understand why your systems are making, especially black box systems, are making the decisions they're making. So with that, I am going to turn it over to Richard.
Thank you very much, Chris. Okay. So what I wanted to talk about today was really talking about a very real and active use case that takes advantage of what we've been talking about today. This is about Jaguar Land Rover in the car, obviously industry, and really also to give a flavor of how they actually started implementing this. Because I think a lot of the time we see a lot of impressive technology, but the question is, how do we implement this in the real situation? How do we introduce new technologies, particularly ones where people can maybe a little bit suspicious? How do you bring it into the business in order to get the sort of advantages that we've been demonstrated today? So for me, certainly at JLR, we started off and we looked at it as a 3-step process. I know that we've talked about the 3-step process before, but just to make it very concrete, we started off with the idea of that first you need to get your data into the system. So this is immediately the first problem. And in order to do that, that takes a certain amount of work. And so particularly also you may have people, the data is in particular silos, people are very proprietary about their data. They don't necessarily want to do this unless they can see that there is a reason for it that is actually going to give some benefit. So the first thing we did was to say, we believe that if we can bring the data together, and the whole point of a graph database in many ways is to link together your disparate data sets in order to get value from the linkage. So we said, what is the big problem that you cannot currently answer? What are the questions that you can't answer? And the first thing they said to us was, we forecast 5 years ahead, and then people don't actually order the cars that we forecast, and so we have to deal with that. And the amount of money involved here is that, and we were looking at originally at about it to see if we could get about $10 million to justify the work that we were going to do. And ultimately, it looked like we could address about $100 million worth of cost, simply due to this variation between forecast and actual orders. And there's a good reason for that, and I'll explain it in later slides. Step 2, once we'd got that, then we said, right, we've got the data in now, we can do more with just the same data. You don't need to do much more work. then we said, what is the next thing that there's likely to be a problem? And they said, well, we've got a problem right now, which is what happens when things go wrong. How do we deal with that? Because the cost of downtime for a car manufacturing line, for example, and this is an estimate, it could be a lot more than this in certain lines, $22,000 per minute. Consider what that means. Losing an entire day is an enormous amount of money. So therefore, spending some money to actually improve the situation, even by a minute, is going to be a good thing. And by a day is a tremendous advantage. And finally, this idea that, okay, so now we've got the end-to-end data visibility, we can now react in real time to issues, which means that we've actually set up the processes so that people actually are interested in seeing the outputs of the system. What happens next? What's the next step? And this is the big one, which Graham has talked about beautifully. But the key point here is optimizing for the best mix. So we have a very complex system, incredibly complex in car manufacturing. And that means that there is a huge amount of hidden risk and indeed hidden profit or indeed hidden agility that may be available if they could just work out how to manage the variation to be able to adjust all of these thousands of parameters that go into making this system work without breaking it. So it's okay changing it, but you also want to know, it was mentioned a couple of times, sensitivity. You want to make sure that the solution that you're coming up with is one that's actually going to be sustainable and that isn't going to be brittle. It isn't just going to break everything when anything goes slightly wrong. And the idea here is that we want to be able to automatically generate future state scenarios with particular desired characteristics and feed that back to the human in the loop so that they can look at that and they can apply their tribal knowledge and all their wisdom, understand what's being recommended and be able to feed back into it and say, okay, this is a good idea or indeed a bad idea. The idea is to give the existing staff superpowers so they can extend, so they can improve, so they can be much better at their jobs. So we're not replacing headcount here, we're just making the business work better. Next slide, please. So this is the particular case study here was actually taken up by Gartner. So I've stolen their slides because I feel that's only fair. And the first thing was this idea, how do we get a clear two-way line of sight between demand and supply? And there is a huge distance between suppliers supplying parts and people ordering cars. And that distance isn't just in terms of the complexity of the mapping between cars as a bunch of parts to the actual parts that are supplied, but also in time. Generally, suppliers need to plan around about 3 to 5 years in advance, which kind of makes sense because say somebody is creating headlights, for example, they have to build an entire factory in order to create the headlights for a particular line of cars. That's not something that you do on a week's notice. That takes years of planning. And so as a result, they have to make forecasts. And of course, demand is never quite what you expect. And indeed, Jaguar found that they predicted that China was going to buy an awful lot of these cars. And I've shown you a picture of this car on the right. This is the Range Rover Evoque. Buy one, it's lovely. Anyway, the key point here is that when it actually came to the demand on the day, it changed. It was actually the US who wanted to buy a load of these, and China didn't want to buy them for various reasons. In the US, the reasons people wanted to buy was because Hollywood, you may have noticed, has completely fallen in love with Range Rovers, and particularly for bad guys. So you'll see all the bad guys now drive Range Rovers, which means that people want to buy Range Rovers because they're cool cars now. So suddenly they had this situation where they'd forecast a load of demand in China, but actually they had to switch demand to the US. And basically these are completely different cars. There is some overlap in terms of parts. I mean, they're basically the same car in terms of the platform, but as far as the styling is concerned, safety features, the particular features that the market likes to have. So in China, they like to have a lot of seats, for example, whereas in the US, they like to have a lot of space. And these are conflicting features, which is going to change things. So the key point here is that if you don't actually consume the parts from a supplier, that will cost more than if you'd actually taken the parts from the supplier, because they will charge you because you've committed to buy the parts, and then they will charge you because now they have to deal with the fact that you're not going to actually take the parts and they still have to make them. for them, it still costs thousands of dollars to actually bring down machines. So they have to make the parts, and then they have to deal with the fact they're made with the parts. So this is where you get penalties if you don't consume parts. What we did was give them visibility into that ahead of time, so that they could actually then go to the suppliers before they'd made the parts and say, look, actually, we're not going to need this many sunroofs, but we are going to need more seats. We're going to need more of these other pieces. Can we come to an arrangement whereby we can switch manufacturing? And the idea is then that you can avoid the cost. The other thing you can do is you can discount the cars you can build into the market. And by doing that, you can essentially change the order book to be able to deal with that. So this is what the visibility gave them, was suddenly they went from only seeing a change in demand and not really knowing what it was going to do to them, to being able to understand exactly what the impact was going to be on the supply chain and what they were going to do about it. Next slide, please. So that comes to the next piece. And here you can see a Range Rover pulling a train. They're very good at pulling things. So a tow bar is a big deal on Range Rovers and Land Rovers. People often use them for pulling their boats, and this demonstration is just an indication of just how seriously they take this. What happened, and this is a real situation, and I'll put a reference at the end where there's a link so that you can go to the use case and you can hear Harry Powell, who's the director of data at JLR. He will describe this exact use case, but I'll give it a little bit of color here. So what happened was that in order to build these cars, they needed tow bars. And when the tow bars arrived, it turned out there'd been some problem with the specification on the tow bars. I have no idea why, but the point was they could not build the cars. Now in manufacturing, remember, you've got to keep the line running. You cannot stop the line, $22,000 a minute. So suddenly they've got a pile of parts that don't work. And so a bunch of cars that they simply cannot manufacture. So how do you deal with this situation? Normally they'd scratch their heads and they'd kind of improvise, but that's never going to work as well. With our system, instead, they asked the question which they could never ask before, which was, which cars are most similar to the cars we were going to build that are in our existing order book? Can we resequence what we build so that we can delay the need for tow bars and give the supplier time to fix what had gone wrong? And this is what they did. Normally, this would take 2 weeks to do this study. And clearly, if your tow bars have arrived on the day, you're not going to have 2 weeks of room in order to make these changes. By using the standard graph algorithms, in this case, similarity algorithms, which have been mentioned earlier, by being able to apply those algorithms, and this was done by the JLR staff themselves, because the products are very easy to consume by the staff. They didn't ring us up and asked us to help. They told us about it afterwards, which was amazing. It showed us that we'd kind of done our job well in training them. It took that time to work out the alternatives from 2 weeks down to 45 minutes. That meant they did not have to stop the line, and so they avoided hundreds of thousands of dollars of cost simply because they could get the information they needed very, very quickly from the model which had been given. Next slide, please. And this brings us to finally to the last one. And as you can see, I've stolen Gartner's slides again. And I think it's because it's actually probably the most exciting possibility here, which Graham has talked about, which is, how can I optimize what I've got? How can I improve my system? How can I deal with the fact that I've got many different dimensions of good here? There's no single good. It used to be that the simplest good was lowest cost, but then it became fastest. But now, in an era of disruption, you've also got to deal with risk. Risk is now the biggest problem that you've got to deal with. And in a forecasting scenario, the risk becomes extreme. The example I gave earlier, that was an entire market that changed, where suddenly they had to, hundreds of thousands of cars had to go from one market to another market and to be altered. Necessarily, that involves a certain amount of cost. But the question was, could we build resilience into the entire end-to-end supply chain? And what we said was, because we have built the end-to-end view, which is the digital twin as we talk about it, was really a very realistic model of what's happening in the world. Because we have staff who now understand how to apply the particular graph algorithms to this data, and we know the data is good data, we can now add in the much more powerful whole graph analytic capabilities, and TigerGraph has this, and it's one reason why we do so well in this, and to be able to drive lots of different scenarios and present them to the executive and say, this is the balance that you can take. Maybe you want to take a little more risk in certain areas. Maybe these are areas where you don't want to take any risk at all. And so therefore it's okay to take a little bit of cost. And so as a result, suddenly we're getting back into the forecast, and we're feeding back into forecasting and allowing them to forecast 5 years ahead and predict exactly how much variation that's going to be. And to the earlier point, we can also tell them how sensitive those models are to changes, so they can get an idea of whether they are in a very safe space or not. So that's yet another dimension they can have, which is degree of safety. So they can have alternate suppliers, for example. They can negotiate with suppliers so that they have variable amounts they can take on any particular model of the car. So this is the place we are with right now with JLR. And they think that this really is the holy grail billion-dollar solution that they are looking for. And it all starts from the first point of getting the data. So hopefully that shows that when you're taking these technologies, you're not buying a simple solution that really gives you, it's a single note solution that only gives you one advantage. And then next time you want to do something else, you need another advantage. What we're showing is this is very much a technology which is enabling these very, very advanced features, and I think delivering on the promise of machine learning and indeed data systems as we see it. And thank you. So very quickly, quick summary. First, 3 steps. Build your supply chain graph. This is your digital twin. We put it in graph because you don't need to normalize it. You can take it directly from whatever data sources you've got, be they relational data stores, be they documentary, whatever. They go straight into the graph, and we simply model them as is. The next thing we do, we link those entities. And at that point, you can check for your data integrity. You can do entity resolution, which is really just making sure that any data which is pointing to the same thing is linked correctly together. And then finally, once you've got that, you've opened up your world to the point where you can do these amazing things that you couldn't do before, such as bottleneck detection, it says here. And there's a whole list here of all the things that are possible once you've actually got to that point. All you need to do is take the first step. And I think that's it of my slides.
All right. So with that, we've had a few questions that have been sort of coming in. There's some links here. Please come visit all of us online. Lots of great content today. Very exciting. So with that, we have a first question. Looks like it's for you, Graham, which is, what are perhaps the most impactful graph algorithms in supply chain?
That is an interesting question. So it depends a lot on the use case, and it also depends on the connectedness of the data. What we find is that algorithms like shortest path are things that really work very natively to be able to sort of identify mathematically the sort of physical relationships inside of a supply chain. But for your specific use case, please reach out and we can go over it.
And I think you listed, there was one of your charts earlier that had all the different algorithms on it. Okay, second question would be for you, Michael. It looks like our company uses SAP, and how easy would it be to plug this in to start using Graph?
Well, first of all, we embrace existing systems. I mean, there's no such thing as a database as an island. We always connect to other systems. We often produce to other systems as well. And in the case of SAP, there's well-known, well-defined access points into SAP's supply chain modules and the other parts of their landscape that makes the most sense in this case. And Expero has a Confluence certified Kafka connector, which can connect to pretty much anything in our world. So we embrace existing systems, and we can enhance and improve them with machine learning and everything else we talked about today. But it's a fairly straightforward proposition to establish a Kafka connection to SAP, bring the data in, and then get to work.
Okay. Next one looks like it might be for Chris, which is the toolkit that you described with TigerGraph. What is that written in, and how easy is that to modify?
So first of all, written in, generally our web components are written in React. They're web components, so we can stretch them across any major library of front-end technology. All the major JavaScript frameworks anyway, but React is the technology of choice. On top of that, a lot of the visualizations are written on top of that layer, but a standard browser can render any of this stuff as I demonstrated. How easy are they to customize? So the toolkit themselves are extensible in that there's a published API for each of the widgets, and there's a fair amount of customization that you can do just by that API. On top of that, Xpero can extend that with custom solutions, as well as off-the-shelf packages that we have, such as Gradient Path for as far as full-blown software solutions.
Okay, fantastic. Richard, a couple of questions for you. We are using 2 terabytes of bill of material and historical data. What size limitations, if any, would TigerGraph have, or what is the speed by which TigerGraph can run?
So we're fully scalable, both up and out. We have installations running 30 terabytes of online data, and that's online data. So we run real time against that. So really, there isn't a limit in terms of data size. Usually the limit comes on how we can optimize the particular algorithms that are associated with that data. But we welcome scale. We love scale because that's where we live. So I don't think there's any scale problem that we have particularly failed on. I know that we have one customer who's now challenging us to see whether we can actually run a petabyte of data, which is quite exciting, actually. We'll see how we can go with that.
Excellent. Second question. Let's see, I lost it here. From a technology stack, how do you work on premise or in the cloud, or both?
We do both. We're seeing that a lot of people are now moving to on-prem. So JLR, for example, uses GCP, so Google Cloud. We have just started putting financial companies onto the cloud now. So clearly the security is a sole problem because we provide all of the security requirements. But having said that, we are a software product. We are very happy to support people who have requirements that mean they need to start on-prem. Really, all we need is a Unix box. As long as it's nothing too exotic, then we can run on it. So we're very happy to do both.
Okay, and then somebody early on published kind of a funny one about graph technology, and I'll turn that around to say, what would set TigerGraph apart from other graph vendors? Sort of what features and things makes TigerGraph different and better, if you will.
Okay, I can take that. Originally, it was speed, scale, and now and power. But we've worked really hard, and people like Xpero are helping us tremendously in this, is to make it more consumable and configurable by the user. So really, we started off just as almost the dragster of the graph world, in the sense that we could go extremely fast in a straight line, but it might be a little bit difficult to drive. That's no longer the case. We're now very good for driving. We've done so much work to get standards into the language. We are working very hard to make this sort of power consumable by basically normal people. And currently, our training program takes, I think it's 2 to 3 weeks. We can get people up and running and producing value. Fantastic.
All right. Well, we're a few minutes over. Great questions today. Fantastic content. Thank you, everybody, for attending. And thank you, panelists, for the great insight.
Thank you so much.
Thank you.
Thank you.